Alright guys, Professor Floyd here. I just wanted to give you an update on homework 8, questions 5 and 6. So question 5 is basically exactly the same as question 4. You use the same approach and everything. All the answers to the first 5 questions or so should be identical. The only thing that really starts to become different is when you get to the exposure fraction. And now you have an exposure limit for a STEL, short-term exposure limit, of 300 parts per million instead of 200 parts per million for a methyl ethyl ketone. So at this point you should find that since your STEL is so high and your 95th percentile is about 255 ppm, then no, you don't have an overabundance of, you don't have an exceedance fraction that's above 5%. It should be around 3 point something percent. I don't remember it offhand, but so in that case, you realize that you're okay, and you can say that you don't have an you're okay, and you don't have too much exposure above the limit. So you shouldn't worry. You don't have an excess liability. You don't have an excess liability of exposures above the short-term exposure limit. So remember, this is assuming that you've already successfully identified the short-term exposures, and you're not just taking a random sample. You're taking a random sample of high concentration short-term exposures. So that's pretty critical. That's not exactly an easy thing to do, but in certain situations it might be possible. Okay, so now we'll move on to number 6, and this was where I asked you to, let's see here, I've got it pulled up. I told you about working at an ink blending facility, which is a real sort of situation that I encountered when I was consulting. And usually the ink contains less than 1% benzene, but in a few special cases the ink's right at 1% benzene. So why this is important is because the benzene standard comes into effect, and certain provisions are sampling provisions are mandated by the benzene standard. I encourage you to take a look at that and just type in OSHA benzene standard and it'll take you straight to it. So what I'm telling you is that one employee is tasked with checking the mixing vats and adding pigment as they need to, and also filling small orders of 5-gallon pails. So you literally have an employee with a hose holding it, something like filling up your gas tank, and usually it's a bigger tank, but with a 5-gallon pail it might not be. And for about 30-40 seconds he's filling up this can, and then he stops, checks it. He's usually got it on a scale. He's actually checking weight instead of volume content, and then he stops when he gets to a certain weight and caps it up. Well, that means he's always standing within arm's reach of this hose. Well, the hose is spouting solvent or ink, and that ink is about 1% benzene, and so as it hits the bottom and you're getting mixing, every unit of volume that goes in is displacing a unit of air. Well, that air is getting saturated pretty quickly with vapor, so the benzene is of concern. The reality is, when somebody's filling, they're not filling with their arm out like this. They're usually filling about like this so that they can see down inside that hole, or they're filling standing like this and they're looking at the scale. But either way, they're usually not at full arm's length. They're usually fairly close. Besides, it's really tiresome to hold your arm out like this. So you're usually going to end up doing something like this or finding a way to rest your arm up. Okay, so what I told you is that your laboratory has a limit of quantification, LOQ, of 2 micrograms for benzene. So what this means is they can probably detect a little bit less than 2 micrograms, but they're not going to give you an actual number below 2 micrograms. So if you give them a sample that's only got 1 liter of air, they're going to tell you that's 2 micrograms per 1 liter. And so you'll get a certain limit of quantification if you wanted to figure that out in a concentration unit. If you took a very large sample, say you have 50 or 80 liters of air collected, then they still can detect just 2 micrograms, but now you've got a bigger denominator, 80 liters. So their limit of detection or limit of quantification is much lower the bigger sample volume that you collect. So what I've asked you for is, does this laboratory have sufficient, no, I'm sorry. What I've asked you is, what is the minimum volume that you can collect and still detect an overexposure? And we're talking about a short-term exposure limit here. So short-term exposure limit or task-based sampling, which is going to be a STEL type sampling. So the short-term exposure limit from OSHA is 5 ppm for benzene. So that's your target concentration, 5 ppm. And you want to know, can I detect an overexposure of 5 ppm? So how much air volume do I need to collect at a certain known concentration to get at least 2 micrograms of whatever the contaminant is, in this case benzene. So this is not really that complicated. The first thing we need to do, we've got our limit of quantification of 2 micrograms. So we also know that our STEL concentration from OSHA, the OSHA STEL, is 5 ppm. So we want to convert this to milligrams per cubic meter. So how are we going to do that? We've done this about 1,000 times. 5 ppm times the molecular weight, which is 78.11, and divided by the molar volume, 24.45. So this should come out, this is a ratio of 3.19, and so this should come out to around 15.97 or 16.0 milligrams per cubic meter. Okay, so now we know our concentration, we have mass per volume, and we know the mass that the laboratory is limited by. So if we do a little bit of adjusting for our units, and so this is the same thing as 1,600 micrograms per cubic meter, or it's actually the same thing as 16 micrograms per liter, just make this 1,000 smaller and this 1,000 smaller, then that would be a pretty useful ratio to use. It just kind of depends on how you want to do things, but anyways, I'm going to do it this way. So now we have 16 micrograms, oops, sorry. We want to structure this. We put our limit of quantification, which is just a mass, divided by our concentration, which is a mass per volume. So this will give us volume. And what really this gives us is our minimum volume that we must collect. So our LOQ is 2 micrograms. Our concentration is 16 micrograms per liter. So this comes out to 0.1252 liters. So at this point, I hope that you can convert between liters and milliliters in your head. Just it's a factor of 1,000. So this is 125.2, but 125 milliliters. So what's the volume what's the minimum volume that you need to collect? 125 milliliters. If you don't collect that much, then you can't even possibly detect an overexposure. If you collect less than that, then you might actually have 5.1 ppm, which is over the limit, but you're still going to get a less than reportable limit when the lab reports it to you, and that's not very useful. Less thans are just not very useful. So in reality, you don't want to be right at this volume with an exposure fraction of 1 or right at the limit. You really want to be at 10% of the limit. Now, I wasn't getting to that much of a nuance for this question. I was really just wanting you guys to recognize the strategy behind seeing that this is a task-based sample, and the task-based samples are short duration sample should go along with a STEL instead of an 8-hour TWA. So we're talking 15-minute sampling here. Okay, so 125 milliliters. So we'll just go ahead and write that down. So the second part of this question was saying, what if you used an OSHA and a 3M organic vapor monitor, OVM 3500, to try to monitor for this exposure? Does it have enough sensitivity? Will you be able to collect enough sample in this 15-minute time period in order to get the this at least 2 micrograms collected? So this is something that's kind of a, not a hot topic, but a point of interest within industrial hygiene and exposure sampling, is that most people feel that diffusive sampling is not appropriate for relatively low concentrations and short duration. And what we'll see is, well, what we'll answer is, do we have enough sensitivity? So 3M has a guidance document. I think it's called the Technical Data Bulletin. If you Google 3M OVM Organic Vapor Monitor 3500 and Technical Data Bulletin or Technical Bulletin, you'll find this. It's an 11-page document, and on page 7, 3M has published some sampling rates as well as other constants and values that are useful for solvents or analytes that have already been validated in their lab for these sampling devices, for these diffusive monitors. So for benzene, the sampling rate is 35.5 milliliters per minute. And maybe it's not exactly 35.5. I don't know, I don't have that information right in front of me, but it's about 35, 36. So it's in that ballpark. What's ideal is for you to have a lab that's actually conducted this independently. But 3M does a really good job with this sort of thing. They want to make sure that people's exposures are accurately measured. So this is not a bad place for us to start. So let's assume that this is true. So we have a volume, we have a sampling rate. If we divide volume by sampling rate, we'll get time, because our sampling rate is volume over time. So what is it? So 125 mils divided by 35.5 mils per minute is going to equal approximately 3.5 minutes. So does this have the ability to at least detect an overexposure? Yes, because this is much less than 15 minutes. Now, if it was right at 15 minutes, it would be just like the previous explanation I said, for section A, that yes, 125 milliliters is the minimum, but we really would like to collect down to 10% of the exposure limit. So if we wanted 10% of the exposure limit, then we would simply need 10 times the length of time, because we would need 10 times the volume. So if that was the case, then we need 35 minutes to get to 0.1 exposure fraction. Obviously, in a 15-minute sample, we don't have enough time to get, we don't have a sufficient sampling rate to get down to 0.1 exposure fraction or 0.5 ppm exposure. But we do have 3.5, and 3.5 over 15 is what? I'm sorry, 15 over 3.5 is somewhere between 4 to 5. So at least we're going to be in the 20 to 30% range. And that's not bad. It's not perfect. It's not ideal. But at least if I was being exposed to, say, 6 ppm, I should be able to detect that, or 7 ppm. Or even if I was being exposed to 3 ppm for this length of time, I should still get meaningful data back from the lab. So you guys thought that this was kind of a complicated question. Some of you guys wanted to go Henry's Law on this. And while I admire you for your tenacity, it's actually just a pretty straightforward explanation. We calculate our volume that's necessary based off of the concentration of the contaminant, and then we calculate the time based off of our sampling rate. So if you're sampling at 200 mils a minute, which is the max of NIOSH method 1501, the max rate for sampling is 200 mils a minute, the minimum is around 50 mils a minute, then you certainly would have had enough sensitivity. But actually, I guess that's about all I have. There's no but to it. So that's how we solved that one.